Hello, my name is Dan Vilenchik, and I will be presenting the following paper which appeared in COLT 2020. PCA, Principal Component Analysis, is a widely used tool in statistics for visualization and dimensionality reduction, but in the high-dimensional setting, it may suffer from what's known as the curse of dimensionality. And here we see an example on the right, a projection on the computed sample PCs, computed from the data, and on the left, a projection on the population PCs. Now, if the sample PCs do not converge to the population PCs, then we get a picture which is inconsistent with the data, with the latent true distribution of the data. To solve this problem of inconsistency, many times regularization is added, and in the context of PCA, this translates to various sparse PCA optimization problems, where sparsity constraints are added. In this case, we see an L0 sparsity constraint. Namely, we are looking for the unit vector which maximizes the variance, but has at most k non-zero entries. While this may solve the consistency, namely the sample PCs do converge to the population PCs, this optimization program is non-convex. Therefore, it's NP-hard, and there is no polynomial time algorithm that easily solves this problem for all instances. Okay, so how to proceed? One way is to use exhaustive search. So to solve this problem, exhaustive search solves this optimization program exactly, but it is good only for small problem sizes. The computational effort increases very sharply as k or p or both increase and becomes prohibitively large for most computers, for all computers. On the other hand, one can use polynomial time heuristics like diagonal thresholding, where you take the k largest entries of the diagonal of the covariance matrix, namely the features with largest variance, or various relaxations of the L0 constraint to L1 constraint, or semi-definite programming relaxations. Now, the polynomial time algorithms have the following reverse S-shaped behavior. As the SNR decreases, the accuracy deteriorates. And let's say that the accuracy is the intersection between the population PC support and the sample PC support, the PC that the algorithm produces. And in many cases, this is an undesirable behavior. And what we want is the following S-shape. We want the accuracy to be fixed, right? We always succeed to recover the right support, and we are willing to pay with running time. So as the SNR decreases, we are willing to increase the running time. And that's called the anytime paradigm. So in this paper, we study a new algorithm which implements this design principle. Namely, we want the algorithm to calibrate the runtime according to the computational resources available. So if indeed you have a large cluster and or you have a lot of cloud computing power, then you want to be able to use it. Or if you have one month until the submission to the conference, you want to use all your computational power to solve the problem in a correct way, to get the picture on the left and not the picture on the right. So here's one way to do it. You can run exhaustive search for this 1 month that you have, and then use preemption. Just stop execution after this time, and the exhaustive search covers what it can in this 1 month. But we can do much better. We present the following algorithm, a variant on the exhaustive search. So, and it's composed of two procedures. We have an envelope procedure here called SSPCA, seed sparse PCA, which goes over all seeds of size k star. K star is typically much smaller than k. And each seed is completed in a greedy fashion using this second procedure here. And at the end, the best solution, best in terms of F2, is returned. So let's look at this greedy SPCA problem. We have a seed S of size k star, which we want to complete to a candidate solution of size k. We have a ranking function F1, which for every variable outside the seed, it gives some utility, and it ranks the variables according to their utility, from highest to lowest. And then you take the variables that have the k minus k star variables with largest utility. So in what follows, and in the paper, we fix F2 to be the leading eigenvalue of the submatrix induced by S, which is thus just the variance explained on this set of variables. And F1, the utility, is simply the covariance of a variable with the average covariance of X with the set S. SSPCA interpolates between the polynomial time algorithms, specifically diagonal thresholding, so when you take no seed, you get diagonal thresholding, and it interpolates it all the way up to the naive exhaustive search. When you take k star to be k, you get the exhaustive search. And as you vary k star, you get a hierarchy of algorithms with an increasing running time, an increasing computational effort. And the scaling of k star, namely the way, the frugal or the right way to increase k star, is computed from the SNR of the problem. And we will soon see the analysis how k star scales as a function of various parameters that control the SNR in the spiked covariance model. And k star increases to allow for complete reconstruction of the support. So we analyze our algorithm in the spiked covariance model, and let's assume that this is the spike, namely this is the leading PC. It has k non-zero entries, and that would be the population covariance matrix, a rank 1 perturbation of, of the identity. Now, the SNR is controlled by both sigma and k. But for the sake of analysis here, let's assume that it's only controlled by k. So our algorithm, in order to succeed to compute the right support, it needs to satisfy two conditions. Two conditions need to hold. One is spectral separation. So here in yellow, we see the right solution, the correct support. And we want this fact to hold. We want that if I and j are two candidate solutions, but I is closer to the spike than j, then the variance explained by I is larger than j. And in fact, you need this property also for the naive exhaustive search to work. The second property is what we call the existence of golden seeds. So you want there to be a set of size k star so that the algorithm completes it, the greedy algorithm, the greedy step completes it to a set which is either identical or with very large intersection with the right support. Right. So if those two conditions are satisfied, then the algorithm succeeds in outputting the right support. And we show how k star should scale so that these two conditions are met. Okay, so let's see what's known for in the spiked covariance model where we analyzed our algorithm. And as we said, let's say that k governs the SNR. As k increases, the SNR decreases. And let's also assume that n equals p. So there's an information limit when k is on the order of n over log p, and the exhaustive search was proven to find the correct support, the spike, all the way up to the information limit. Way below the information limit, there is a computational phase transition where polynomial time algorithms succeed up to the threshold, and no polynomial time algorithm is known to succeed from this square root n computational limit up to the information limit. Let's see what we found for our algorithm. So when k star equals to 0, we said that that's simply the diagonal thresholding algorithm. And this is already known that it succeeds in recovering the right support, a square root log p factor below the computational threshold. To go all the way to the computational threshold, we need k star to be log n. So we have a quasi-polynomial time algorithms, but simulations shows that even for a very large problem size, namely n equals p equals 20,000, or k star equals 1 suffices. Now, in the interesting regime, that's the weak SNR regime, where no polynomial time algorithm works, we show that K star scales as n to the 2 epsilons time log n, where epsilon is the addition above the threshold. So K is, we parameterize K as n to the half plus epsilon, and this is probably tight, as recent results by Ding et al. Suggest. So to conclude, we show that SSPCA scales exponentially with K over square root n square rather than exponentially with K, like the naive exhaustive search, which is much better. Simulation that we ran corroborate and show how this calibration principle is manifested. So here, for example, we see parameterization which gives which is in the weak SNR regime, namely the regime where polynomial time algorithms perform bad. So we take n equals p equals 1000, k equals 8, and sigma equals a half, should be sigma. So we see that our algorithm, as we increase k star, then the accuracy increases. And here you have a parallel running time. So this is 3 hours on 90 cores. On the other hand, we see diagonal thresholding, we see LARS, covariance thresholding, all are polynomial time algorithms that perform pretty bad because we are in the weak SNR regime. And on the other hand, we see the exhaustive search, which was allowed the same amount of time as our algorithm with a seed of size 3, with k star equals 3, both ran in parallel for 3 hours and were preempted at the end. And we see that the our greedy approach of completing small seeds gave much better results. Thank you very much for listening.